All right. So today we're going to start looking in a little more detail. We're going to get some more detailed SQL examples. So I thought that we could get this going by looking at a database, which I have called bad database. So maybe this is bad, maybe this isn't. But could someone kind of tell me what this database, what the job of this database is?
Looks like to track item orders by customers.
Yeah.
Okay. Yeah. So what kind of application would this be serving?
Maybe inventory for a store.
Yeah. It could be inventory. It could be an e-commerce site. Yeah. It could be lots of things, but that's the basic idea. So we have information about orders. We have information about items, and information about customers. So just looking at that initially, if you were to describe, so what is a row in this database?
A customer.
A customer, okay. So a row is a customer. So we do have customers. We have like a name and an address and an age, but we also have like order items. Is that a customer?
The customer's purchase.
A customer's purchase? Yeah, I think that could work. So a customer's purchase. But so if we think about in general programming, we want to write functions that just do one thing. There's a preference for making things kind of atomic and modular and as simple as possible. If we look at this row in this database, I mean, how many different entities could you pick out if you were going to turn this into a class? How many different classes would you make?
Like just under address, is that what you're talking about? If we turn address or the whole row?
No, the whole row.
Probably a customer and an order.
Two.
Okay, so we could have a customer, we could have an order.
Maybe also an item.
Item, yeah. So we could potentially have customer, we could have order, maybe we could write some of this stuff down. So customer, order, item. Okay, so what are the specific attributes? Again, if this were a class, then what properties would a customer have?
ID,
Okay,
name,
okay,
address, age, and birthday.
okay. I think my editor thinks I'm doing YAML. Okay, so customer has ID, name, address, age, and birthday. And then an order. Or how about item?
Number, cost.
Okay,
Maybe description.
let's say that's the same as an ID. Okay, description. So that's not in this table, but we could definitely, that's something that would work. So item, so someone said one other thing, sorry,
Cost,
cost, okay.
price.
Okay. So we have a customer that I think that's a pretty clear entity item. I think that's also a pretty clear entity and order. It's maybe a little more abstract. So what information does an order need to have?
The item and quantity.
Okay.
Maybe also the customer ID.
Okay. So an order maybe belongs to a customer or is associated with a customer. Okay. Yeah, so what about address? So I think this is good. So we could definitely pull out these entities, but if we wanted to, like, you know, really go all out, is address, I mean, could we think of address as being its own entity as well?
Yeah, because you can separate by address and then city and state.
Yeah, so address, so if we think of, if this were a class, right? If this were a class and we just pass in address, that's just a string, right? So there isn't really any structure there. It's just a string. And it would be pretty easy, I think, to make a mistake. Or what if you have an apartment number? Like, how do you parse an address? If you're just given a string, how do you parse an address out of that? It's actually a pretty complicated question, especially if you think about, you know, all the different kind, like PO boxes and suites and apartment numbers and, you know, something and a half, or, you know, international addresses. So it gets, you know, it can get pretty complicated. So just relying on a string here, you know, might not cut it. So we could definitely add an address. I won't go into all the detail here, but we could have like a street number. And then there are questions about if we want to be able to represent an, you know, an address anywhere in the world, what do we use? What about province? Like the US doesn't have provinces, but other, you know, Canada has provinces. So how do we handle that? Do we have, you know, do we have a column for province for any possible value that could exist anywhere in the world and then just not use it most of the time?
Could you just put it with state? I mean, state and province, that's kind of Canada's provinces are similar to states, right?
Yeah, you could do state, you know, or province, something like that, maybe. But that, you know, that could create issues. Maybe there's a case where, you know, province doesn't directly map on to state somewhere else in the world, or even Canada. I'm not, you know, I don't really know about Canada specifically, but that may end up creating a problem or may end up forcing your application into one direction, and you have to do some very hacky logic somewhere to compensate for this database decision later on. So there isn't necessarily a right answer, but these are all problems, and these problems, a lot of times these things seem simple or straightforward, but once you actually get down to the nitty gritty of how am I actually going to use this data, and what happens if my, you know, my business goes international, or what happens if I start using lots of different kinds of customers and so on. So even something like an address can get very complicated, and we could take the address and we could even split up the address into further tables, like states. So we could have a state, there's only 50 states, right? So here, if we have 1 billion customers, each customer has an address which has a state. So we're storing information about, New York, a billion times, when really there's only 50, let's say 50 states, but we keep storing that value over and over and over and over again. And what happens if someone, what happens if there's an error in the application and someone, I don't think NB is a state. What happens if someone does that? Are we going to know about it? So how you kind of think of entities, you can really go nuts. You don't have to go fully, full nuts. But it's good to think about entities. So something like this is probably not going to work for a few reasons. So you can imagine at the very beginning, if you set up your own business, this is probably how you might want to start tracking orders initially. You have a spreadsheet, and then you have all the information that you need for every single order. And then what happens when Sally Smith orders something else? Well, you just add an entry. So that's Sally Smith. And then she orders a table. And let's just say that's order number 3. And so I don't know, 100. Actually, maybe this would be 300. Okay. So we do something like this. Okay. So that's not too bad. But what happens when we have millions of customers and billions of orders? Well, now we're repeating this same information over and over again. So if we're talking about storage space and cost and things like that, at scale, these things become significant. So we're storing a whole bunch of redundant data now. Like we have Sally Smith's name twice, we have her address twice, we have her age twice, her birthday twice. So we don't really need that information to be duplicated. Another issue is that, let's say Sally Smith gets married. So I don't know. Danish, is that a last name? I don't know. Sally Danish. So she gets married. So now we have another name here. So do we know that this is the same person? Is this the same person or is this a different person?
They have the same ID.
Okay, so that's a great question. So what is this ID for? If I didn't update this, so that's my fault. But so now I've kind of answered the question. But what is this ID for?
To associate person.
Looks like it's just
create a
counting.
unique. Yeah, I guess you could have the multiple people with the same name. So if you had multiple Sally Smiths, you wouldn't have.
Yeah. So if we think about, again, this is connected to the question of what is a row? What does a row represent in this database?
Order entries.
Yeah, so it's kind of a tough question to answer because we have so many entities here. We could say, customer orders or something like that. And so the grain of the table, the granularity of the table, or the question, what is a row? What does a row represent? Is, I would say, something like, customer order, although it's more complicated. And this ID identifies a given row. So this is a way to give a unique identifier to every single row here. So the problem with when Sally changes her name is that our application doesn't really handle that. So if we're entering this by hand or something, we can say, oh, I know that this is Sally, so maybe I can just, do I go and change her name everywhere? So I do a search for Sally Danish and then replace it with, or Sally Smith and replace it with Sally Danish. And I can update these values. You could do that, but that, you're introducing, the possibility of error creeping in. I could just, another alternative would be that I change nothing and maybe I just have a post-it note on my computer and I say, Sally Smith is the same person as Sally Danish. That's also not a viable solution and it doesn't scale at all. So yeah, we have so that's one problem, is that because we have this redundant data, if anything changes, we now have multiple versions of the same data. So we can't really trust our database anymore. So another issue, so we're repeating stuff, which could introduce bugs if anything changes or needs to be modified. What about order item? Is there a limitation here?
Well, yeah, because the same customer can order 15 items, and then you have to make an entry for every one of those.
Yeah.
Or are the lamps the same lamps, or they're different kinds of lamps? There's no description. There's no way to uniquely identify the types of stuff being sold.
Okay, good. So those are both good points. So one is concern for uniqueness, and that kind of relates to this question over here. But yeah, in general, we want an individual row in a table to be unique. And if there are multiple things called lamp, that might create some ambiguity, which could be a problem. The other thing is that, yeah, what happens if you want to order a lamp and a table? I guess you could do like something like that.
Yeah, but then order item cost would get kind of messy. I guess you could do the same thing, like 45 comma 100, but
Yeah. So this is, we've kind of, the way we've designed our database here, we've kind of painted ourselves into a corner where now an order can really only have one item associated with it. So you could create multiple orders. So if Sally wants a lamp and a table, you could just create more entries. But we have this problem where, again, maybe we're repeating information, and how do we know that this belongs to one order? How do we know if it's 30 orders or one order with 30 items in it? So there are, there are a number of problems with the way that this is currently set up, and the way that you solve those problems is basically by thinking carefully about the entities you want to represent. And we're not going to get into like the nitty gritty of, so there's, if you're interested in this, you can look up normal forms. What you want, that there are a few different levels, but like the third normal form is what you want. It basically says that you basically things should be unique. They should all kind of belong. Every column should kind of belong to the same entity. So here we have customer, and then we also have orders and order information. So those are two different entities in the same row. So you don't want to do that. You also don't want to do things, you want every value to be atomic. So you don't want to do things like have two different values here. So there there is an array data type in most database implementations, but that's kind of a special case. So you want to make sure that there's only one piece of information in every cell. And that also applies to the address here. And even name. Even name, we could break up into another entity that has first, last, suffix, title, whatever. So most of it will be, most of this kind of thinking should be basically familiar from just general software engineering principles that we've already been exposed to. And some of it is specific to databases. So what I'd like to do now is maybe pull out some of the stuff and start over and redesign this database, or maybe some simplified version of this. Yeah, so we'll do that. And the tool I'm going to use here is something called Quick Database Diagrams. There's a link to this in the challenge. You don't have to use this specific tool, but you almost, I would strongly encourage you to draw out your entities and how they're connected. It just makes things much easier than trying to track everything in your head. Okay. So when we're designing a database, the first thing we're going to do is we're going to try and extract all of the entities we're going to want. So just focus on what are the entities that I am going to need, and then after that, we'll look at how they're connected. So first step is just the entities. So we look here, maybe I'll just use this. We'll start with customer. So there's a little bit of like some specific, like, you know, a domain specific syntax here, but you don't need to worry about learning. I wouldn't waste time like learning how to use this particular tool, but you can. So we're going to need a customer. What else are we going to need? We're going to need an order. We'll do item, order. And then there's a question. So I'm not going to worry about the address. I'm not going to get into the nitty gritty. I'm just going to assume that a customer, you know, is its own entity. We have an item and an order. So I'm going to add some minimal fields here. So for everything, I'm going to add an ID. You don't have to do that, but the reason I'm doing that is because when we get to Django, that's just how Django works. So every entity is going to have its own unique identifier. So that's not always 100% best practice with a database creating a separate column that will uniquely identify every row. Usually you want to use what's called a natural key or some combination of things, like data that already exists, rather than creating a new artificial column. But just so you know. Okay, and then this is going to be, I'm going to mark this as PK, which means primary key. So we didn't talk about keys on Wednesday. On Wednesday, kind of avoided doing that. So if we have two tables that are going to be connected, we usually want to mark those values as having a key. And the primary key, there are a few different kinds of keys. The primary key is a way to uniquely identify a given row. So that's what the primary key is for. The primary key, in this case, it's just going to be a number, so an integer. So the first row will be 1, the second row will be 2, and so on. It'll just increment. You can also use, as I said, a natural key. So if, for example, you have a system where you require a user's email. So if you assume that, you know, every email is unique, then you could use that as a primary key. So if I identify customers by their email, or a combination of email and name, or email and birthday, or whatever, some combination of columns that is, you know, that's meaningfully unique for the given application, then you can do that. Okay, so ID, artificial primary key, so I can uniquely identify every row. And then customer, let's just say name, and that's going to be varchar, which is just string. So I think I'm just going to leave that. I'm going to try to keep the fields as simple as possible, because I'm more concerned about how these are connected. Okay, so we have a customer, and then an item. So this is, you know, some product, you know, table, chair, whatever. So I'm also going to give this an ID, so I can uniquely identify every row. And then I'll just call item name. I could also use name, but just to avoid some potential ambiguity there. And I'll make this varchar. And then order. In order. So what should an order have in it?
Quantity.
Quantity. Okay, sure. An order could have quantity. So there's an issue. So the way that this database is set up right now, as I said, we don't really have a way to have multiple items per order. So if we think about, you can start thinking about the relationship between some of these things. So if we say, what's the relationship between a customer and an order?
Is that 1-to-1? Since there's one customer per order and every order needs a customer?
Okay, good. So a customer, so a given order should belong to just one customer, right? Let's say, I mean, we could definitely imagine an application where that's not the case. If you have like a, I don't know, like a check splitting app or something like that, an order could belong to multiple customers potentially. But let's just say normal. This is a normal application, and an order is associated with just one customer. But you said 1-to-1, so it's definitely one in that direction. What about customer to order? Can a customer have multiple orders?
Oh yes, that would be 1-to-many, right?
Yeah. So there are basically 3 kinds of relationships that entities can have in a database. There's 1-to-1, which is not that common. We won't worry about that right now. And 1-to-many, which is the most common, which is something like that. So an order is associated with one customer, and a customer can be associated with many orders. So that's 1-to-many. So we can actually mark that here. So we have an order and a customer, and we can say that a customer, an order is associated, an order basically belongs to a given customer. So we're going to mark that here. An order is going to have a customer ID. I'll do an ID. It's also going to have a customer. And this customer ID needs to line up with this, right? So customer ID needs to line up with orders customer ID. So what we did on Wednesday is we just left that as it is, and when you try to join these two tables, you can just see if they're equal, and that works fine. But SQL has a way to specifically mark that these entities are connected, and it does that with something called a foreign key. So foreign key, So this would be an example of a foreign key. So it's foreign because it basically is it's connected to another table. So table outside of itself. So you mark this as a foreign key, which I think is how you do that. And there's some specific notation here, so don't worry about that. And then this will be okay. So I'm gonna reverse this relationship. Yeah. That does. Oops. Let's see, customer has. Okay, good. All right, so the syntax here is just specific to this application, so I wouldn't worry about that. But when you read something like this, notice on this end, there's little crow's feet. There's like 3 little things. There's crow's feet over here, and then over here, it's just 1 bar. So this is somewhat standard notation to describe the kind of relationship you have. So one, these entities are connected. So that's at a high level, you can see that that's happening. So customer and order are connected. The other thing is that a customer can have many orders. So that's what this crow's feet. So you read it going from customer to order. That's a many relationship. So a customer can have many orders. And if we go the other way, an order can have 1 customer. So a given order belongs to just 1 customer. So that's this single bar and then the crow's feet here. So some of this notation, again, this is, you don't need to like memorize this in particular. This is somewhat standard. It's probably good to be familiar with, but you don't need to become an expert. Okay, so now we can see that a customer belongs to an order, and but so we have that relationship, so that's okay. What about item? Does item have a relationship to customer?
I'd say maybe indirectly through the order, but I could be wrong.
Yeah, I think that's right. So I can't think of a scenario where we would really want in our database an item to belong to a given customer or customer to be associated with a given item. That just doesn't make sense. So from our business side, like the customer is, the item, like from our inventory control perspective, like, our items have nothing to do with customers, right? And then they're only kind of associated temporarily if they actually make an order. But again, I think that's through the order. Now the order and item, on the other hand, I think they do have a relationship. So what's the relationship between an order and an item?
Well, one order can have multiple items.
Okay. So in this version of our database, that's not the case, right? In this version of our database, an order can just have 1 item. An item could still belong to multiple orders though, right? So here we have lamp. We have multiple orders with lamp, but a given order only has 1 item in it. So the way that this is currently implemented, what kind of relationship do we have between order and item?
One
So-
to many.
Yeah, it's a 1 to many. So the way that this is currently set up is an order has 1 item, but an item can belong to multiple orders. So an order has 1 item, but an item can have many orders, be associated with many orders. So that's a 1 to many relationship, which is just, it's like this relationship, but that's not, I think that's not what we want here. You could do that. You could restrict, could have an e-commerce application where you can only ever order 1 thing, but might not be the best strategy. So we have what kind of, so we have one to many, we have many to many. Can anyone guess what the third kind of relationship is?
Many to one.
So okay, so that's definitely a good thought. So that's kind of so if we talk about the relationship between order and customer, so it's a one to many this way, and it's a many to one this way. So one to many and many to one, it's basically the same thing. It just depends on, you know, the order that you're the order of the relationship.
What about a no relationship status?
Yeah, I mean, I guess you could potentially have a table that's, you know, purely isolated. I guess that something like this might be, there's no relationship to any other table. I guess you could do that. Yeah, I hadn't thought of that as a specific type, but I think you could do that. Yeah.
Many to many, right?
Yeah, yeah. So what those are good answers, but yeah, what I was looking for was many to many. So we have one to many here, and we have many. So we can have an order can have many items, which that's what we want, right? If we're running an e-commerce site, we want people to put as many things in their shopping cart as possible. So order can have lots of items, and an item can be associated with multiple orders. So lots of people can order lamps. So an order has lots of items, and an item has or is associated with lots of orders. So how do we represent that? Well, it's a little tricky. Here, for example, if we look at order and customer, if it's one to many, it's easy. We just we'll just stamp order with a customer ID. Okay, every order has one customer ID. Boom, right there. Now, what if every item has multiple orders? You can't really do that. One, because every grid here, every box here should be atomic. So we shouldn't be messing with lists or arrays here. So the way you solve this problem is actually by creating a third table. So we can't really directly represent a many to many relationship here. We're going to have to create another table, which is going to connect orders and items. And we can call it, you know, whatever you want, but I'm going to call it order items. So often the convention would be to use both names, except one of them is plural, like order items or item orders, whatever makes sense. So I'm going to call it order items. And the job of the order items table is going to be to connect order to item. So it's going to have, I'll just give it an ID because everything will have an ID. And then it's going to need two foreign keys. It's going to need a foreign key to connect it to order and a foreign key to connect it to item. So I can add that here. So I'll call it order underscore ID. And this will be a foreign key. And it's going to connect to order.id. So an order could have many items. So this is the relationship here. It's a little funny to read, but once we get it all hooked up, hopefully it'll make a little bit more sense. And then we're also going to need to connect item in here. So we'll have an item, an order items, we'll have an item ID. And that will be okay. So now the way that this is set up is a customer can have many orders. A given order is associated with just one customer. And an order can have lots of items, and an item can belong to lots of orders. So what order items allows you to do is, let me see if I can do this here. So order items is just going to be like a join table. So if I have an order, I'm trying to think of the best way to do this. If I have an order and it has an ID, this is a given order, and name. Actually, I'm going to represent this as a tuple. So if I have an order and it's ID of 1, and then I have a customer. So we haven't filled out all these fields yet, but we'll have a customer ID 1, let's say, and then I have item. And an item is going to have an ID and a name. So 1. And I'll add another item. 2, and yeah, we'll say that these belong. So 2 orders from the same customer. So the first order, the second order, they both belong to the same customer, customer number 1. We have 2 items. So now if we have order items, we can now say that a given, so we can associate it with this order ID 1. So this order ID 1 can have this item ID. So you can order a hammer. Let me do, sorry, change this. So this is, I know these are all numbers, so it's a little hard to see, but an order ID. So this is someone ordering a hammer. This is an order for a hammer. And we can have the same order now, but also add a nail. So now this order is one entity. This is one order with an ID of 1 associated with just one customer, customer number 1. And because we have this other table, we can associate multiple items with this given order. So this is order number 1, but we can add as many items as we want to this table. So every item associated with a given order will have its own row in the order items table. So that's probably a little confusing, but it'll make more sense when you start talking about queries. We'll see how things are connected when we join tables. Now, just to talk about kind of the potential downsides here. One of the advantages of this, even though there's some obvious disadvantages, one advantage is it's all just one big table, right? So you can just take a look at it and see basically everything that you need. And even if we did it like this, it's still, it's still pretty clear. So now we can have multiple items associated with a given order, and we can see everything there. There's some problems, but it's also easy, and it's easier to query. So if I want to get all of Sally's orders, I just do a search, and maybe I have to account for her name change or whatever, so I just add that to the filter. But basically, it's just one query. Now the problem with this, if I want to get all of Sally's, if I want to get all of the items that Sally has ever ordered, I just will filter by name, and I filter by order item, and then I just get like maybe the unique set of everything in this column. So it's a pretty simple operation. Over here though, with this structure, if I want to get all of the items that Sally has ever ordered, well, I start here. Here's Sally over here, and here are the items over here. So I have to go through all of this. I have to go through these other tables in order to get that. So it makes the query a lot more complicated. The positive side of this is that I have much better data integrity. I'm using less space. I'm not storing redundant information. All these other advantages, but the disadvantage is now I have a more complex structure, and querying requires joining potentially multiple tables. Okay, I think now's probably a good time for a 10-minute break. Yes, we'll come back at 9 o'clock Central. Okay, so let's see. Let's come back. We have our schema, order items, item. So maybe we can add a couple things. I think order, I'm just going to leave as it is. Item name. Yeah. Actually, I think this should probably be good enough. This is like the absolute bare minimum. Obviously, in real life, you'd want to have more information about all of these things, but I think this is fine for now. So what I'm going to do is I'm going to take a screenshot of this, and then we can go here and then write the actual SQL for this. Let's see. All right. So here is split. All right. So here is our database schema that we have. So let's go ahead and create those tables. All right. So to create the tables, we're going to use the create table statement from SQL. So create, I'll still do caps today, but I'll probably stop doing that soon. So create table. I'll create the customer first. And then I have to pass in the name of the column and the type, the data type that I want to store in the column. So let's just say that I want to have an ID for every single one of these, and I want it to be I want Postgres to take care of managing that for me. So there's a way to do that. So I'll create a column called ID, and I'll make it a primary key. And doing that provides a couple benefits we'll talk about in a second. And I'll make this serial, which is just a Postgres type saying basically increment that. Every time I create a new row, increment this ID 1. And then the other thing is going to be names. And that's going to be varchar. Let's say 100, somewhat arbitrary. All right. So this is the first table. So I'm going to go ahead and run this script, and we'll take a look at it. So first thing I'm going to do, I'll create a database. So PS or create DB, and we can call this online shop. And then I'm going to execute this script inside this database. So PSQL online shop, and then -F, I'm going to pass it a file. And the file is going to be the create table script. Okay. So I've got an issue here. Let's see, syntax at or near primary. The one thing is I'm going to need a colon here, but I may have messed up the order here. Let me just try running this one more time. Yes. Okay, so the error messages are often not helpful. Syntax at or near primary. So what I'm going to do is I'm going to look up primary key Postgres. Okay, so let's see. So I can create a table, primary key. So there's a few different ways to do this. So I need data type primary key. So I think I just need to switch serial and primary key. Oops. Let's try that. Okay, so this worked. So the type, so this is a special type in Postgres, which is an auto incrementing integer. And then we have I'm marking this as a primary key. Now marking this as a primary key does a couple things. One, it basically requires this value to be unique. So I can't have multiple threes in there. If I try to insert a record that has an ID that already exists, it won't let me do it. So I get some data integrity there. I can avoid duplication. And another side benefit, which we're not going to talk about, is that it will create an index. So it makes looking for this value faster, but we don't need to worry about that. Okay, so I'm going to go ahead and take a look at the table inside of Postgres. So PSQL online shop. And I'm going to describe this. So I have this customer table that I've created. So I'll describe the customer table. So /d customer. And I can see that this ID, it's a type of integer. So I didn't specify integer. I just said it was the serial type, but serial type uses integer. And it added this constraint, not null. So by using serial, you can think of it as like a function or a built-in something, which is going to do a few things. It's going to make it an integer. It's going to make it not null, so I can't not have a value here. And then the default value. So if I don't give it a value, if I create a row without providing an ID, then it's going to use this by default, which is a function, next val. So you don't need to worry about this, or how it works, but it's just gonna auto increment. Every time I insert a record, it's gonna add 1. So I don't have to manage this. Postgres is gonna manage this for me. The other thing is I have this name, which we've seen before. It's character. It's a string, and then there's indexes. You don't need to worry about that, but it created this customer PK index based on the primary key. You do not need to worry about this at all, but just I'll just say for the sake of saying it. So an index is basically another table, which is just a lookup. So if I want to search, if I create my customer table and I add 1,000,000 rows to it, and I say, give me row 500,000. Well, the entries are not guaranteed to be, they're not ordered basically. So it's not like give me entry 500,000 and then it's not like looking up something in an array. That doesn't work that way. So Postgres is gonna have to scan everything, every row, in order to find that. So you want to avoid that. So what an index does is it creates another table, which is just a lookup table. So it can immediately look up that value, and then that will reference a spot that'll reference the actual spot where it's stored in the database, so it can just jump immediately there. So it doesn't have to scan the entire table. So that's why that's there. In the a B tree, this is the structure that's used to create the index. So you don't need to worry about what that is, but it's basically just a tree. And so we've seen trees before, and traversing trees is often an efficient way to search for things. Okay, so we can get out of this. So I'm going to create the other tables now. So I've got customer. So now I'm going to create order. And I'll give this an ID, serial primary key. And we'll give it a customer ID. Now, this is a little tricky because customer ID is a foreign key, right? So customer ID is really a reference to this customer table. It's really a reference to this field right here. So the way we can do that is we know from looking at the database that this is an integer type. So customer ID is also going to be an integer type. So make this an integer type. And then what we can do is in another step, so we're going to kind of create this, and then after we create it, we're going to say, hey, this is actually a foreign key. So we can look up, let's see. So we create this as an integer field, and then it's, I forget the syntax, foreign key references. I'll just look this up real quick. So foreign key. Okay, so you do foreign key, and then the column references, blah, blah, blah. Okay. For foreign key. And then we're going to pass it this right here. This is the foreign key right here, customer ID. And then we're going to say what this is actually connected to. So this references customer.id. So we can do references customer.id. I think this has to be in parentheses as well. Okay. So I'm also going to add these drop table statements just, while we're developing, so I can rerun this over and over again. So drop. I'm going to do this in lowercase, drop table exists. I think there's actually an issue with order being like a keyword, but yeah, I think order is a keyword or something. So I'm just gonna make this plural for the sake of getting past this. Okay, so I created this table, and then I get an issue, syntax, blah, blah, blah. So we'll see if the semicolon was the issue. It was not. Syntax at or near this, foreign key, customer ID, references, something. So it looks like there's an issue here. So I look back, references, parent table. So I need to not do this dot syntax. But it's going to be customer, and then I pass in the ID here. Okay, so now this works, and we can go in and take a look at the database. There you go. And I can describe all the tables, and I have customer and orders. So I'm going to take a look at orders. And I can see that there's this ID, which is auto incrementing, just like the other one, and then indexes, just like we saw before. And then we also have this new thing, which is foreign key constraints. So customer orders, customer ID, F key, you don't need to worry about that. This is a foreign key, customer ID references customer ID. So now Postgres knows that these tables are connected. So before, like on Wednesday, we just created 2 independent tables, and then when we query them, we just happened to know how they were supposed to be connected. But this way, when you use a foreign key, you can explicitly mark that these tables are connected, which is it's a more accurate description of your application. It also helps Postgres be more efficient when it queries stuff. Okay, so we've got customer, we've got order, we could do item. And we need an ID, serial, primary key, and then item name. Okay, so that's I think pretty straightforward. And then this order items table. And this is basically, this only exists because we can't directly express many-to-many relationships. So we're creating this table, which is just going to join the order and the items tables. So ID, serial, primary key. And then we're going to have order ID, and that's going to be an integer because the field that it refers to is an integer. And then item ID integer. And then we're going to mark these as foreign keys. So for key, and this will be order ID references. So this is connected to the orders ID. And the other foreign key, this is going to be item ID. This is going to reference item ID. All right, and I'm going to add some more drop table statements here. Quit out of this, and I'll run this. Okay. So I have an error here. I have an error here. It says error cannot drop table customer because other objects depend on it. So I'm saying it's on this line, it's trying to drop customer, but other things are depending on it. So what else is depending on customer?
Orders.
Yeah. Yeah, so this is one reason to explicitly mark your relationships using foreign keys, because if you try to do something like this, like if I have an order that belongs to a customer and I delete that customer, then what do I basically have an orphaned record somewhere. So I have a record with a foreign key that refers to something which now doesn't exist. So there's a few things you might want to do to handle that, but it's at least marked. So the database knows that these are connected, so maybe you don't want to do this. I'm just gonna, you can actually add this cascade. keyword, and it will just delete everything. So I'm going to do that for now. Okay. So I now have these tables created. All right, so we can insert some records. All right, another script here. Okay, so I'm going to insert in, I'll create customer records first. So insert, I'm going to do lowercase here, into customer, and we have to pass it the fields that we want. So customer has an ID and a name, but we don't need to worry about the ID because Postgres is going to take care of that. So we can ignore that and just pass in name. And then values. So values, if you see, I think someone is not muted. So values will have some customer names. So Bob, we'll just create 2 customers. Bob and Sally. And then we could create some items. So insert. So one thing to pay attention to as you're doing this, the order can be significant, right? So if you had created these tables in a different order, it might have been an issue. If you create a table that depends on something else, there's a way to handle that, but I don't want to go into it, but just something to be aware of if you encounter that problem. So item has ID and item name, but we're not going to worry about ID because Postgres takes care of that. So item name is the column, and then values. Let's insert some records. Hammer. Table. Okay, so now we have customers and we have some items. So in order, we could create an order, insert into orders, which is actually called orders now for. So ID, customer ID. So order doesn't really have like its own value. We could definitely add something to this, like order date or shipping address or whatever. But we're not going to worry about that. So order is just going to have a customer ID. And this is a little weird, but we're going to have to just understand that Postgres is going to make this ID 1 and this ID 2. So if we want this order to belong to Bob, then we have to give it a 1. So let's do customer ID. So Bob has 2 orders, and let's say Sally has 1 order. Okay, so now we have Bob and Sally, we have our items, and we have our orders. So now we basically need to populate all of the items that belong to a given order. So insert into order items. This will have an order ID and an item ID. We're going to do this on a new line. Okay, so the order ID and the item ID, this is what allows us to associate multiple items with a given order. So if we have order, let's say order number 1, because that's the primary key for order. So order number 1, which is this order. I know this is a little weird. We're using primary keys, but so it's this first order because that's going to be auto-generated. So we're going to say this order items thing. So this is the first item for the first order. So in item ID, let's say it's 1, 2, let's say it's 3. And then so on Bob's first order, he orders a table, and then he also orders, let's say, a hammer. So 1, 1. Okay, so that's Bob's first order, and then Bob's second order. Let's say he orders. This is order number 2, and he orders a hammer and nails. So item 1, and then he also orders nails, which is 2. And then for the third order, so that's Sally's order. So Sally is number 2. So the third order, which belongs to Sally, let's say she orders everything. So 1. So if you find this kind of baffling and bizarre, I can sympathize. You know, that's how it is. So you have to know that we're creating IDs, and then you have to kind of track those as you're inserting this data. And hopefully I did that right. We'll see. Easy things grow. So I've created this. So I'm going to go ahead and insert the record. So PSQL. What do we call this database? Online shop. Okay. So line 3. Let's see.
I think it's the commas
The commas.
in the order items. I think it's complaining about the commas in the values section,
At the at the
or
end
the
of
lack of
order.
commas rather between the order items.
Like here. Oh yeah. Thank you.
No problem.
All right, let's try that one more time. Okay, cool. So I'm going to just recreate the database in case some of that data was duplicated. So I'm going to drop everything, recreate the tables, and then reinsert the records. And it looks like that worked. So let's write some queries so we can double check. So, all right, so first, I'm just going to do select star from all the tables just to see if that works. So select star from customer, select star from order, select star from order items. I don't think it's case sensitive, but select star from SQL online shop, pass it a file, and that will be the queries. Okay. So the first one, the customer worked. It's like I have an issue with order because it's called orders. Try running that again. Okay, so here's the customer. Here's the orders. Here's the order items. And here's the actual items. So this order items table, this joining table, or this, this table that enables many-to-many relationship, you can see that for a given order ID, like order 1. So everything that has an order ID of 1 is the same order. but there's multiple items. And just you know, let's just say this order items table, if this had 1 billion rows or something, and you were just wanting to do an initial, like you've never seen this table before and you just want to check it out, you can also do, you can add limit. So instead of actually looking through everything, it'll just grab the first 3. So that table does that. Just FYI. Okay. All right, so we have all of our tables now. So let's say so we can let's ask and answer a few questions. So first off, let's get all of our customers. Actually, let's get a count of all of our customers. Okay, we'll get the customers first, and then the count. So get all customer names. So how would I write that query?
Is it select customer dot name from the
Okay.
table?
Yeah.
Something.
Yeah, so name, I could just use name because there's no ambiguity, but yeah, you could also specify it. So select name from customer. You can run that query. And then we get the names. Okay, so we have all of our customers' names right here. What if we don't care about the names? Maybe we have, you know, like 500,000, so we don't really care about the names. We just want to know how many customers do we have?
Return the primary or return the key from the very last customer.
I think there's a count.
Max,
Like,
max or something like that.
Yeah, so so that is definitely a good thought, you know, returning the key from the last customer. The problem with that is you can't really know what the last customer is. Yeah,
would it be okay?
Yeah.
Would it be select count name from customer?
Yeah. So there are, so we saw, I don't know if I can scroll up. Yeah. So here's the auto incrementing ID that we're getting for the primary key. You can see that it looks like a function, right? So Postgres has functions built into it, and this is one, next value. You don't worry about it, but there's a function. So there are a whole bunch of functions you can use to help you do kind of basic things. One of them is count. So there are aggregations. They're called aggregations, and this is one of them. Count. It's built in, and you can pass it a column name. I'm just going to do all the columns from customer. And this doesn't have to be capitalized, but okay. So notice that it returned something that has a column called count. So it just made that up, count, as 2. So there are 2 customers. Now, if I don't like this name, this is not meaningful to me. I want to do, I'll call it like total customers. So I can rename this. I can either just do as, which is maybe the better way to do it. So I'm giving this an alias, or it will actually accept you just pass it just like that, and it will know that this is the renamed value. So you can do that. Okay, so let's do, I want to know how many orders does Bob have? Oops. So first question is, what tables am I going to have to access in order to answer this question?
And order
Probably-
items and customer.
Can you say that again?
Order items and customer.
So I don't actually care about the items, I just care about the orders. So I just want to know, how many orders does Bob have? I actually don't care about what he ordered.
Just orders and customer.
Yeah, so I think we're gonna have to query both of these. So how do you write a query that involves two tables?
That would join.
Yeah. So we're gonna have to join these two tables. So these two tables exist as independent entities in the database, but when we're querying them, we need them to we basically need to reconstitute one table that uses both of them. So we'll join. So for now, we'll just select everything, but we can make refinements. So select star from, you can start with either table. Most of the time it doesn't matter. So select everything from customer. And then we're going to select this customer table and we're going to join it to the order table. So join orders. And then you need to tell it what to use. So it's going to look for an expression basically that evaluates to true or false. And if it's true, it's going to connect the rows, and if it's not, then it's not going to. So we know how order and customer are connected, right? So how are order and customer connected?
With the ID.
Yeah. So the customer's ID should match the order's customer ID. So it's a little confusing because we have, ID and customer repeated a lot, but this is customer's primary key. That's the ID. And here is the foreign key in orders, which references the customer ID. So this tells us that an order is associated with one customer. So it's like the customer is stamping the order with their key. Okay, so we're going to select everything from customer. We're going to join orders on this customer. So we're going to make sure that everything lines up. So let's just see what we get here. Whoops. So I forgot the equal sign here. And it's just the single equal, so not the double or triple. Okay. So now I have this kind of super table, which is a combination of the customer and the order. So here's Bob and the customer ID. So ID is ambiguous, but we know that this is the order ID. So order has ID and customer ID, ID and customer ID, and this ID is for the customer. So yeah, it's very confusing. You can try different naming conventions, but you're at some level you're kind of stuck with this problem. Okay, so we've got our customer and then we've got the order. So I only care about Bob. So how can I eliminate anyone who isn't Bob?
Where name equals Bob.
Okay, yeah, exactly. So I'll do where. So where is the filter? So where name, and I can double check the columns. In this case, there's no ambiguity. Name only exists once. Otherwise, I might have to specify, customer dot name. but I can just get away with this. So name, single equals, and then Bob. I'll add a semicolon and run this. Okay, so now it's the same, but we only have Bob. So we're getting there. So how many orders does Bob have? Well, I mean, we can kind of look at, because this is a very small table, we can kind of just answer it by counting the rows. But if this had 2.5 billion rows or something, you probably wouldn't want to try to hand count that. So how can we get an answer which tells us how many results we have here?
Can you wrap line 17 and count?
Okay, so that's definitely the right idea. That's not syntactically how you do it, but that's the idea. So just like here, so we kind of have the answer implicitly here. So what we want is how many rows. We've filtered down, we've joined and filtered our data to the data set we want, but we don't actually care about the particular data anymore. We just want the question is basically how many rows do we have here? And there is a way to get the count of that, and you just do that right here. So count. And there's 2. And we should be able to change this to Sally and get 1. So if you want to know how many orders Bob has, we know that Bob is a customer and that an order is going to belong to this order table. So we know we're going to have to deal with 2 tables, which means we're going to have to join them. So we can just write that immediately. And then once we have the joined tables, that's all of the possible data we could have. We need to whittle that down to Bob or Sally, whoever we're dealing with. So you can use a where clause for that. And then depending on what else you're doing, you can also, the syntax for this just happens to be use count here. And this will stand for all the rows. So any row, there's some nuance here, but we don't need to worry about that. So you can just use count star if you want to get the count. Okay. So let's do one more. Not how many orders does Bob have. Let's do how many items has Sally ordered? So what tables are we going to need?
I'm thinking customer, order, and order items.
Okay, so yeah, so at a very basic level, we're talking about how many items has Sally ordered. So we have to somehow get maybe item, or actually, sorry, I don't want to do this because you are correct, but which items? Yes, so your answer is correct. So I'm going to make this slightly harder, and we're going to have to go all the way to the item table. So we have a customer, so we know we have a customer, that's Sally. So we're gonna have to get information from this, and we have items, so we're gonna have to have this. The problem is there isn't a direct connection between customer and item. So because we have this all diagrammed out, it's much easier to see, but we're gonna have to, in order to go from customer to item, we're gonna have to go from customer to order, and then order connects to order items, and then order items connects to item. So we're gonna have to do a lot of joining, which is, you know, kind of a pain. It's kind of ugly. It's one of the downsides of relational databases, but yeah. But you can join as many things as you want. So don't be intimidated by joins. Okay, so which items? So I'm just gonna kind of break this down into smaller steps. So for now, we'll just select everything. Select star from, well, we can start at customer, why not? And then we're gonna join order. And how are we gonna join order? No, orders. So how does customer connect to order?
Customer ID and
The ID.
orders ID.
Yep. So customer dot ID equals orders customer ID. Okay, good. So now we've got these tables connected, but that's not enough. We're gonna have to also join order items. So join order items on. And how are we going to join? What's the connection between order items and order?
So order ID and the order items order ID.
Yeah, that's real fun to say. So orders ID equals order items dot order ID. Okay, there's one reason why it's way easier to have this drawn out. You can keep referring to this. So customer, you don't have to think about it too much. Okay, customer is connected to order. ID is customer ID. Order is connected to order items. ID is order ID, and then we just keep following the chain. So order items is connected to item. Well, let's just take a look at this so far. So here's what we have so far. It's kind of a mess, but that's what we've got so far. So we're at customer order items. So let's keep going now. Join item, and that's going to be on order. And it doesn't matter. Like the order here doesn't matter. So whether you do orders.customer ID equals customer ID or the reverse, it doesn't make any difference. So items dot item ID equals item dot ID. All right, so I'll run this query, and now we have a very big table, which, yeah. So another thing to note is that when you do a select, it will return a table basically. So SQL will treat this as a table. So you can actually do recursive queries. You can write a query that returns a table, and then you can write a query on that result. We're not going to worry about that right now, but you can do that. So we have this, you know, table, which is our result set. And so what do we care about?
The names.
Items.
Yes. So the first thing we care about is the name. So we just care about Sally. And then the other thing we care about is way at the other end, the item name. So first thing, we can drop everyone who isn't Sally. How do we filter?
Where name equals Sally.
Okay. Yep. Where name is Sally, and we can just do a quick scan. If there is ambiguity in the column name, it'll throw an error, but we can just do a quick name. So name looks like it's unique among columns, so we're good there. Let's see this result set. Okay, good. So we just have Sally. Do we care about any of these other values right here? Yeah, I don't think we care about those. So I only care about the items that Sally has ordered.
Could you get the items but their ID? Since we have an item ID, or you have to go directly to the name?
So you can grab the name here just from this column.
So we can select just item name.
Yeah.
If we want just that.
Yep. So we start off with this kind of master result set. So this, you can think of SQL queries as, you know, you start with this huge mess and you just gradually make it smaller and smaller and smaller. So here, this is like all of the data we could possibly need, right? And out of all of that possible data, we really just need this. So we're not going to select everything. We're going to select item name. And those are the 3 items that Sally ordered. And if we wanted to, we could do something like Sally's items.
Is there a way to write it? I know there is a way, but to write it so that if we had multiple hammer orders, it would only return one name instead
Yeah.
of all the different.
Yes, there is. So I'm gonna do so let's just say that Sally orders another hammer. 3, 1. And I'm gonna drop the database and recreate it somewhere around here. There we go. Insert records. Okay, and then if you write the query. So here we added, so Sally ordered 2 hammers in this order. So that shows up. So maybe we don't need this duplicate. We don't just want every item that she ordered. We want every unique item, or every type of item, or however you want to say that. So you can do that. There's actually a keyword you can specify, which is distinct. So instead of just select item name, you can do select distinct item name. And instead of getting these 4, the second hammer should get dropped. So for those of you who are not thrilled right now, I would say that this is, more complex probably than you'll ever really need to do for this course. Something like this. If you can do stuff like this, this is roughly where, the kind of minimum that you need to know for the course. But you should also not be intimidated by joins, especially if you're diagramming things out. If you're diagramming things out, you should be able to just kind of mindlessly write stuff like this. Okay. Yeah, that's all I got for today. We're here.